Welcome to SIMBa seminar. We are so pleased to have Miquel Saucedo here, who is going to talk us about the subcritical uncertainty principle for the Fourier transform. Thank you so much.
Thank you, Avi. So this is joint work with my supervisor, Sergei Ikhonov. And well, okay, so since the results of this talk will slightly depend on the choice of Fourier transform, I want to make it clear from the beginning that this will be our normalization. So with a 2 pi in the exponent. And just so that you know, in particular, the Fourier transform of this function, the standard Gaussian, will be itself. So let us now begin. The uncertainty principles are a family of results which make this general idea precise that it's impossible for both a function and its Fourier transform to be simultaneously localized or small. And there are many results of this type. For instance, the most famous one is the Heisenberg uncertainty principle. But for this talk, the most relevant ones will be the Hardy and the Cowling-Price uncertainty principle. Well, the Hardy is essentially a characterization of Gaussians. So as I mentioned before, the Fourier transform of a Gaussian is a Gaussian. And what Hardy tells us is that the Gaussian is the only function which is pointwise dominated by a Gaussian and whose Fourier transform is also pointwise dominated by a Gaussian. Okay, so by pointwise domination, I mean this. That this time, this exponential is bounded. And well, this result was later generalized to the LP setting by Cowling and Price. And in this case, if instead of L infinity domination, we have LP domination, in this sense, then the function must vanish identically. And well, these results also have some manifestations in PDEs. And for instance, let us consider the Schrödinger equation for the harmonic oscillator. Then, using the very close connection between the propagator of this equation, so between the solutions of the Schrödinger equation for the harmonic oscillator and the Fourier transform, one can rewrite actually the Hardy uncertainty principle in this way. So assume that we have a solution for the Schrödinger equation, and we know that at the initial time, it decays like a Gaussian, so like this. And at some other time, time 1, it also decays like a Gaussian. And now, using the fact that evolving a solution 1 second is equivalent to taking the Fourier transform, this is just because of the Schrödinger equation for the harmonic oscillator, it turns out that one can reformulate the Hardy principle in this way. So under these conditions, then we know what the solution is. There's just one possible solution, of course, up to a constant. So this is, once again, nothing more than the Hardy uncertainty principle reformulated. So let us now relax a little bit our hypothesis and consider what is called the subcritical case. So now, instead of imposing that the solution must decay like a Gaussian at 2 different times, we say that it decays a little bit slower than a Gaussian. So here, in case you don't see, that's a red epsilon. Okay, so the decay is a little bit smaller. So one can easily see that the space of solutions to this Schrödinger equation, which satisfy these 2 conditions, is actually huge. So it contains, of course, Gaussians, but also translations of Gaussians or polynomials times Gaussians. It's a huge space, and in particular, from these 2 pieces of information, we will not be able to fully recover the solution. But now, what Vemuri realized was that these constraints imply that the solution must exhibit some very strong decay at all times. And he conjectured what this decay should be. Well, this result was conjectured by Vemuri, and then Kulikov, Oliveira, and Ramos found or proved the sharp decay conjectured by Vemuri by all times except for 1 time. And this result has been recently settled by Radchenko and Ramos for every time. And what this tells us is that if at initial time and other time it decays like this slower exponential, then for any other time it must have this also exponential lag decay for explicit and sharp time-independent exponent. Okay, so this problem is solved. And well, also what Kulikov, Oliveira, and Ramos realized was that if one is willing to accept a constant in the exponent, which depends on time, one should be able to improve this result. They obtained some bounds, and moreover, they conjectured what the sharp time-dependent constant should be. So this is an explicit, very complicated expression, but the important thing is that in some way it interpolates between the hypothesis. So at initial time and at the final time, we know the decay. So here, when t is 0 or 1, we should get this number here. And then at the worst possible time, so the time in the middle, we should recover the sharp time-independent constant. So they suggest explicit constant with interpolation between the initial conditions and the time-independent result. This has not been proved. And well, in connection with this result, they formulated the following theorem, which can be understood as a subcritical version of the Cowling price uncertainty principle. So let us recall what the Cowling price uncertainty principle tells us. So it's here. Have a function which is LP dominated by a Gaussian in both function and Fourier side, then the function vanishes identically. So let us now consider the subcritical case, so with slightly relaxed constraints. Okay, so we have once again the red epsilon. So now the function need not vanish. But what they found was that it must have some very strong decay. And here what's important to note is that they proved that the function must have this Gaussian type decay, but slightly slower than the one given in this exponent. So since epsilon prime is larger than epsilon, here there's epsilon prime, this number is a little bit lower, a little bit smaller, okay? So they proved this. And of course, what they asked was whether one could remove this loss in the exponent, which is this question. And this is what we have been working on. And our answer to this question is that this is almost possible, in the sense that one can remove the epsilon loss in the exponent. So we have the same conditions. We have removed the epsilon loss in the exponent, but one must always pay the price of having a polynomial loss. Okay, and moreover, this is sharp, so this cannot be improved in any way. The sharp pointwise decay is this one. Okay, and well, since this will be late.
Should it be 1 over p instead of minus 1 over p?
No, it's minus 1 over p. It's a little bit
less than 1, right?
This is a little bit. So this function decays or does not increase larger than this. Does not increase faster than this to 1 over p. So this is not bounded. If we remove this, it is not bounded. To make it bounded, we need to multiply it by a decreasing function.
Okay.
Which is this one.
Okay, I see.
That's why I say it's almost true. It's true up to polynomial thing. Well, since we will need it later on, I just want to remark that using some standard, the standard uniform boundedness principle, one can translate this implication into an inequality. Okay, this is just some technical, simple fact. Okay, and well, as a first application of our result, which translates between LP domination and L infinity domination without loss in the exponent, we are able to prove the Cowling price principle, which was about LP domination, assuming the Hardy principle, which is about L infinity domination. And this is very simple. So just assuming this LP domination, by our result, we have L infinity domination. But now Hardy, or a version of the Hardy principle I previously stated, tells us that under these conditions, the function must be a multiple of a Gaussian. And well, the integrability condition already forces this constant to be 0. So any such function must vanish. Okay, let us now give an idea of the proof of this result in a very particular case, which is when p is equal to 2. In this case, the situation is especially nice because the result follows from this general lemma. And well, the lemma is very similar to what we want to prove. Okay, so we want to prove, look at this inequality. So we have function with some weight, function weight, function weight. Here we have the same thing, but instead of this exponential, we have power. And here what is most important is that the fact that this constant here is not allowed to depend on the degree of the polynomial, okay? And well, assuming this lemma, it's straightforward to deduce our main result, because we will recall that we want to bound this quantity, and then just write the exponential as a power series. Here, and then using the fact that the constant does not depend on the degree of the polynomial, we can just apply this inequality to the whole sum. We arrive here, and finally, all that remains is to sum this series. Okay, so if we believe this lemma, this is our main lemma, then the result follows in a straightforward way. Moreover, Here, we don't use many properties about the exponential. Yes, that it has a power series expansion with non-negative coefficients. So it's clear that one can obtain similar results for more general functions. So for instance, instead of here we have 2, we could put 3 or 4 or anything. Okay, so it's very general. This is our, as I mentioned, it is our main lemma, but we have also obtained a complementary lemma, which is very similar to the one before. The only difference is here on the left-hand side. So here, so let's go back. Here we have something which depended on x, okay? Now it's gone, but we have something very large, which depends on m. And as you can see, sometimes this lemma will be better depending on the particular relation between x and m. So if m is very, very big, this will be better. And if x is very, very big compared to m, the other one will be better. And I think that this lemma is interesting because it also gives proof of the Cowling price principle using the same power series idea as the one I mentioned before. And it's basically the same. So assuming that this quantity is finite, we write everything as a power series and then apply this lemma to the whole sum. We write here. And now this quantity should be finite. So then if alpha is too big, this sum will be infinite. So the only way for this to be true is that the function vanishes identical. So this allows us to prove a weaker version of the Cowling price, or a Cowling price without sharp constant. So we know that the sharp constant is 1. So we know that if this happens for alpha greater than 1, this is 0. But what we've proved using this method is that this happens for large enough alpha. So this is not too nice, but the good thing is that this method is, once again, very, very general. So it works for any function with non-negative power series expansion, okay? So there's some trade-off here. Okay, so as I mentioned many times, the main point or the main advantage of our lemma is the fact that it's this inequality, but with a constant which does not depend on m, okay? Because so let's recall the lemma. We were here. The constant here does not depend on m. And this was very important to apply the inequality to the whole sum. Here I want to show you that if one doesn't care about that, if one is willing to work with a constant which depends on m, the situation is very, very simple. Why? So use the Fourier inversion formula here and take some phi, which is a very nice function. So here we have the same, and from here to here we use Plancherel. And now we use Cauchy's balance. So this is the this is the right-hand side, and we want to choose phi, which makes this quantity small. Here it's fairly standard to just use a bump function. So this is just a function, in this case, which in the Fourier side behaves, probably speaking, like an indicator function, and in the function side, it also behaves, roughly speaking, like an indicator function. And of course, we know that this is not possible. This is forbidden by the certainty principle, but this can make true up to some, say, polynomial tail. And the point is that since we're working here with polynomial weights, we can always make the polynomial tail decay much, much faster than the polynomials, than the weight, and the weight does not see this decay. Okay? So it is fairly simple, but the constant that one obtains depends on m. And well, we want to obtain this result instead of with polynomial weights, with exponential weights. But this is, so we cannot make a bump function decay like exponential. This is forbidden by the certainty principle. So that's the main point of our result. And well, the idea is to choose a better choice of function phi here, And well, what we do is to let us look for functions which are compactly supported on an interval of length minus delta delta. With delta will be a parameter to be defined later. And then any such function can be written in this way. So this is just a convenient way to write a compactly supported function. Okay, but this is just a general function. And well, recall that here we had two terms, a Fourier term and a function term. We want them to be small. So to make the Fourier term small, a way is to assume that the Fourier transform is very flat near the origin. Okay, so it's 1 up to a very high degree near the origin. And we're using the relation between the Fourier transform and the function, so the derivative of the Fourier transform on the function, this is equivalent to this. Okay, this is just Fourier inversion formula. And now we impose that our desired phi should satisfy this property, and then we look for the function phi, which makes this second term, the function term, the smallest possible. And to do so, we just choose the function g, with the minimal norm this, which is exactly equal to this norm. And well, this is nothing but a geometry problem or a linear algebra problem. We're imposing some linear conditions and we are looking for the smallest Euclidean norm. This is a very simple problem. And actually the solution is just given by what's called the reproducing kernel of this space. So the reproducing kernel, K, this, is the unique polynomial of degree m which satisfies this condition here. So if instead of G we have K here, we have this. And this is called, of course, reproducing because integrating against K reproduces the value of the polynomial at 0.0. Okay, so this reproducing kernel gives us this, and now all that remains is to compute this minimum. So to compute the norm of the reproducing kernel with this weight, which we will simply call the norm. So let us now see how one can compute this quantity. So to do so, we use what's called the variational characterization of the reproducing kernel, which is nothing but this very simple identity over here. So 1 over the norm of the reproducing kernel is the minimum of the norms of any polynomial up to a certain degree, which is 1 at 0. So this may seem very confusing, but this is nothing but Cauchy-Schwarz, okay? So let us, using the reproducing kernel property, this is just polynomial at 0. And now we use Cauchy-Schwarz here. And this is nothing but a very complicated way of writing down this simple estimate. So in other words, this means that if an inequality of this type holds, this is called a Nikolsky type inequality with a certain constant, then the very same constant also bounds the reproducing kernel. And moreover, the best constant here, so the smallest constant in the Nikolsky inequality is actually the norm of the reproducing kernel. This is just once again, okay? So the Nikolsky type inequalities, fortunately, are very well studied. So in particular, for our case, it was good enough to use this result. So with this constant, which was obtained by Nevai, Elderly, and Magnus, okay? So these are all the ingredients that we need to deal with the case P equals 2. So what remains is to do some computations. So now let us say a word about the LP case, because here we used, here, there is some L2 filling, there is some geometry here. So what can we do in the LP setting? There are no reproducing kernels, but fortunately, there are something which is sometimes good enough. Okay, so recall the variational characterization of the reproducing kernel, which is this, which was nothing but Cauchy-Schwarz in disguise. And this problem makes sense for LP as well. Okay, so let us consider the very same problem for LP. Now, let us take the minimizer, which we called PM, and now construct this function. Now, what happens if P is 2? If P is 2, this is out, so we just get a polynomial, which is a reproducing kernel. If P is not 2, this, for instance, if P is 1, say, well, this is not a polynomial, but this still has this reproducing property. Okay, so it's a kind of reproducing kernel which does not lie quite in the space, but it has still this reproducing property. And the proof of this fact is actually also very simple. Okay, it's something very, very well known. I can show it to you in just one line. So take the minimizer. Okay, so we take the minimizer polynomial, the minimizer of all the polynomials which satisfy this. Take any other polynomial. Now, this function, as a function of lambda, has a minimum at 0. Okay, so if we take the derivative with respect to lambda, at lambda equals to 0, should be 0. But what is the derivative? You can just take the derivative without paying much attention to any possible problem. And this is, what is this? Derivative p minus 1, okay? This. And this, now by some simple change of variable, we can just obtain the reproducing property, okay? So it's something very, very simple. And using this and some modification of this idea, we are able to prove with the desired result, which I recall was this estimate, which then allows us to prove this implication, okay? So this is the proof of this implication. Let us now check the sharpness. By sharpness, it's clear what I mean. So I have here that this cannot be removed. Okay, so you cannot say that this implies that this function is bounded. You need something else. So let us see how we can do it. As before, let us start by considering the simpler case of polynomial weights. Now, in this case, the situation is very, very simple. Okay, because once again, we can use this trick of bump functions, which behave, roughly speaking, like characteristic function if we work with polynomial weights. So in this case, we take this bump function, which is concentrated around x naught, and whose Fourier transform is the characteristic function. So here, the uncertainty principle forces that if the width of this is 1 over x naught, the width of this should be x naught. Okay, and this gives you some constraint, but then you can just pretend these and these are indicator functions because the polynomial weight does not see this decay and just obtain what we want. Okay, so this is also very, very simple. Now, what happens here? As before, we cannot do this trick about bump functions because of the exponential decay. So we have to do something else. And here I want to explain you how it works in a very, very, very particular case, in which, for some magic, we have some explicit formulas for everything. Which is p equals to, but now alpha, so there was an alpha in the exponent of the exponential, is this number, this magic number. And well, write our function f in this way, as an change of variable. Then, using the relation between the Fourier transform of the product and the convolution of the Fourier transform, one can write the function in this way. Okay, so this is simple. And now, this quantity over here, what happens? This is a square, so we can just expand this square. Okay. If there's something unclear, please tell me. Okay, and now, what we're going to do is to do some rearrangement of integrals, some Fubini, and after some very cumbersome computation, one actually arrives to this nice formula over here. Of course, we're always assuming that G hat is very, very nice, so you can assume it's smooth, compactly supported, and everything that you need. Well, here we use the power series expansion of the exponential to write this in this way. But this is nothing but the derivative of the function g at 0. And by doing these computations, we were able to translate this more difficult inequality into this inequality, in which every term that matters can be seen easily. So here it's an interplay between the value of g at point x, the L2 norm of g, and this term which implies the derivatives at 0. Okay, so now we are going to do something very similar to what we did at the beginning. We once again look for functions which are band limited. And the idea is to find the h function which suits our purposes the best. So recall that there were three terms: the value of the function at 0 at x, the L2 norm at the derivatives. So we impose that the function at point x is 1. Then to make the derivative terms small, we say that lots of derivatives of this function should vanish. So lots of derivatives means from 0 to capital N, where capital N will be defined later. And well, in the Fourier side, this can be written in this way. So h hat is orthogonal to many polynomials, to any polynomial of degree n. And well, among all these functions, we want to make this middle term the smallest. And once again, this is a linear algebra problem, a geometry problem. We are imposing some linear equations and we are looking for the minimal L2 norm. So one can solve this problem actually exactly. And it turns out that the solution is very much related to the projection of the exponential, this exponential, onto the set of polynomials. So P star, I didn't say it, it's a projection of this function onto the set of polynomials up to degree n. So the solution is the distance between the exponential and its projection. Okay, so this is the projection onto the orthogonal set, if you wish, suitably rescaled. So we want to estimate this function from the norm of this function. So recall that it was this g here. Oops, this g here from above, because it was here, the right-hand side. Since this quantity is in the denominator, we want to estimate this quantity from below. Okay. So the point is, we would like that the exponential cannot be approximated by polynomials of certain degree. And this is the content of our next lemma, which is to estimate the error between the exponential and its projection, and to see that this error should be considerable. And well, just for simplicity, forget about all the constants and just study the general problem of approximating an exponential function oscillating at frequency capital D by polynomials up to a certain degree. And well, if we don't want the exponential to be approximated, there's something more or less intuitive, that is that if the exponential oscillates at frequency D, the polynomial should also have degree D, okay? Because frequency D means D oscillations, and degree D means, roughly speaking, also D oscillations. So if the polynomial has degree less than the frequency, we are not going to be able to approximate our exponential in any meaningful way. And this is what this lemma tells us. So, okay, here I put this number. This is just the trivial approximation. So here we just give up and we just take polynomial to be 0. What is the error? Well, the error is the two norm of the exponential, which is this one. And what this tells us is that if the degree is too small, any approximation is not much better than just this trivial approximation. Okay, and finally, let us give an idea of the proof of this result. So here we use some results from approximation theory, which relate one quantity, which is called the modulus of smoothness, or the modulus of continuity, with, okay, you didn't mention it. So this En, this is called the least error of approximation. Okay, this is because of the relation between the projection and the best approximation. The projection is the best approximation in the L to norm. Okay. So what this result in approximation theory relates the best approximation is by or with the modulus of oscillation, modulus of continuity. And well, what is, roughly speaking, the modulus of continuity? So this tells us how much a function differs from a translate. So a function here, you move it a little bit and compare it with respect to the original function. Now, a smooth function should be very close to its translate. Okay, so this means that a very smooth function should have a very small modulus of smoothness. And well, what is the modulus of smoothness of an exponential which oscillates at frequency D? Because I can also make a picture here. Okay, so we just minus 1, 1. It oscillates at frequency D. This means that the period is 1 over D. This length is 1 over D. And this means that if you move the function, you translate the function by a distance half of the period, you get minus the same function. If you translate it by a function, the period, you get the same function. Okay, so what does it mean in terms of the modulus of smoothness? It means that the modulus of smoothness at step 1 over D is just 1. Okay, so the function translated 1 over the period is very, very different. It's the opposite of the original function. Okay, so this is a way of codifying this idea that oscillating exponential of frequency D oscillates at frequency D. And well, using this fact together with this lemma from approximation theory, we are able to show that the least error of approximation, so the best approximation, is just bad. And well, using this, we have all the ingredients already available. So after some computations, we are able to obtain our result in this special case. Okay. And now what happens in the general case? Because I want to remind you that everything that we did here was for this very special case for which we had some very nice formulas. But what can we do in general? So well, it turns out that we were lucky and the previous construction, or something very close to the previous construction, also works in the general case. So let us see why. We have, as before, our h function. So this function whose Fourier transform was orthogonal to many polynomials, and we multiply it by an exponential. Now, this h function has lots of cancellation available. So we want to use this cancellation. And a way to do this is by, once again, we take the Fourier transform. The Fourier transform is the convolution. And now we use the cancellation. So this is orthogonal to many polynomials. This means that here we can put any polynomial, and this will be equal. And now all that remains is to approximate the Gaussian, this Gaussian, as well as we can by polynomials. And by doing this, we will obtain we will get that the Fourier transform is very, very small. Okay, so using this and some related ideas, we are able to obtain the result in the general case. So well, to sum up, the main result of this presentation was this inequality, okay? Which tells us that if we have some domination in the L2 sense, we can translate it into L infinity domination independently of the degree of the polynomial, but we always must pay this price. And we also had this complementary result in which this weight in the left-hand side can be replaced by some other thing, which, as I mentioned many times, here it's better. When m is very large, this is better. When x is very large, this is better. And moreover, using these two general results, we were able to show that L2 domination translates into L infinity domination with this loss for a very large class of weights. So from this directly, we have for polynomials. We have for polynomials, for power series with positive coefficients, going up to exponentials, up to the subcritical case. So recall that in the calling price case, we have that for the standard Gaussian, the function must vanish. But up to this case, we have this, and this is sharp. And then suddenly, if we go to this critical calling price case, then any function in this space must be trivial. And this, or a weaker version of this, could be proved by using this result. And now what I think is interesting is to know that here there's some kind of jump. So we had this result for many, many functions, starting from the lowest, from polynomials to exponentials, up to the critical case minus epsilon. And suddenly we go beyond and we just get 0. So a question that I have is whether there is some smooth transition between these two regimes. So, in other words, whether there is some weight for which L2 domination translates into L infinity domination, and this is sharp. Okay, so this will be something in the middle, because here we have this loss, but here we have nothing. Okay, so that's a question I would have. And with this, I finish my presentation. Thank you very much.
I want to ask you about the second part of the talk, like the sharpness of the result. Like, could you explain like backwards a bit, because you said sharpness in the beginning and then you explained the construction. Can you go briefly on how this construction proves the sharpness?
How this construction proves the sharpness? Okay. So we are here. We want to prove that this number over here is sharp. And we constructed a function for which this quantity is 1. This quantity is very, very small because of the derivative thing. So all that remains is to compare this g of x with the L2 norm of g. Okay? So we had, for our particular construction, we had that lots of derivatives vanish.
Yeah.
So just believe me that this term is negligible for this case.
Yeah.
We have n factorial, and here the n factorial wins, kills everything.
Okay.
So we just have to compare g of x with the norm of g. Okay? So we have this term, and this term. This term disappears.
But I mean, what you're trying to prove is that the factor in the left is necessary, right?
Yes. So we are going to so the function will be 1 here, and this quantity will be 1 over square root of x.
The norm of g depends on x.
The norm of the function g will depend on x. Yes. For x, yeah, okay, that's a good point. For
So
x, we construct a function.
Yeah. That depends on x.
Yeah, of course. Yeah.
Yeah,
that's a good point.
okay.
Yeah. For if x, there's no way that this is saturated at every point.
Okay,
For
okay,
each
okay.
x, we can construct the function. Yeah, right. Yeah, no.
Okay.